under the cover of darkness, the world lies hidden from view. Without light, I've no idea what lies beyond my immediate surroundings. I'm closed in, enveloped on all sides by the unknown. For much of human history, when the sun went down and the dark set in, we were at the mercy of the night. But over the centuries, we've developed our own sources of illumination. We've lit our homes, our streets, our cities, and in doing so, we've banished the darkness into the shadows. And just as we've used light to illuminate our world, the more we've discovered about light's properties, the more of the universe it's shown us. We've seen into the depths of space and back to the beginning of time. But as we've looked deeper, we've come to realize how little we've seen, and that the cosmos's greatest mysteries remain hidden in the dark. Light and dark is essentially the story of everything we know and everything we don't know about our universe. And it all begins with light. It's such an integral part of the way we perceive the world, it's easy to take it for granted. But for centuries, understanding what light really is has been one of science's most enduring questions. The first steps towards understanding the properties of light were made in the 3rd century BC by the renowned Greek mathematician Euclid. And he did it by thinking about something so obvious that most of us don't give it any thought at all. Placing the tiny chair very close to the camera produces a large image on the retina. And because we're not used to seeing tiny chairs in everyday life, our brains are tricked into thinking it's a normal-sized chair in the middle of the room. And the reason this illusion works at all is because to judge distances, our brains rely on a simple fact. The further away things are, the smaller they appear to the eye. And it was by focusing on exactly why distant objects could appear the same size as much smaller ones closer up that led Euclid to discover one of light's most fundamental properties. Obviously, the London Eye is much bigger than my fingers, I know that. And yet, to me, they look the same size. So how do we explain this? Well, Euclid came up with an elegant solution. For my finger to appear at the top of the wheel, my eye, my finger, and the top of the wheel must all lie on the same line.
But Euclid's insight didn't just explain the tricks of perspective. It revealed a basic truth about light itself.
Euclid had discovered that light travels in straight lines.
Realizing how it travels marks the beginning of our scientific understanding of light. And it also meant that if we could divert it from its straight line path, we could change the way we see the world. But that leap wouldn't happen for another 2,000 years. It was eventually made in Renaissance Italy by one of the founding fathers of modern science. In the summer of 1609, Galileo Galilei made the short but fateful journey from his home in Padua to Venice, capital of the Venetian Republic.
Galileo had flame-red hair, a full beard, and was well known for his love of fine wines and generous hospitality, and also for his anti-establishment views. By this time, he'd also built up a reputation as a natural philosopher and mathematician, and he was regarded as a valuable asset to the Venetian Republic.
But although, as a professor, he had a regular income, Galileo was never far from financial troubles.
When his father died in 1591, Galileo, the eldest of 4 surviving siblings, became head of the household and effectively took on responsibility for supporting his brother, a poor itinerant musician, and for paying his sister's dowries. By the time he came to Venice, he still owed a significant amount of money to his 2 brothers-in-law, and so was always on the lookout for a money-making scheme.
And that summer, Venice was abuzz with rumors of a device that appeared to do the impossible. A Dutch spyglass that could bring distant objects closer. It was just the opportunity Galileo was looking for.
Back in the 17th century, the spyglass was cutting-edge technology, and details of how it worked were a closely guarded secret. All Galileo knew was that it consisted of 2 lenses arranged in a tube. And so when he developed his own, he kept it very secret as well. But we do know from a shopping list that he got his glass from the small island of Murano out in the lagoon. And because no tools existed, he had to improvise. For instance, buying an artillery ball to grind the curved surfaces of the lenses.
It had been known since the first spectacles were produced in the middle of the 13th century that glass had the strange property of bending light. But unlike spectacles, the spyglass, an early telescope, required a combination of lenses in a very specific arrangement.
This is how Galileo's telescope works. Rays of light come in from a distant object, so they're almost parallel, where they meet his first lens. This is the objective lens, and it's plano-convex, which means it's flat on one side and curved on the other. It's the sort of lens used to treat long-sightedness. What it does is bend the rays of light towards each other so that they would meet at a point. But before this focal point, Galileo places his second lens, the ocular lens, which is plano-concave. And this bends the rays of light back out again so that they emerge parallel where they enter the eye. And then the eye's lens focuses them on the retina. Now, the magnification of a telescope depends on the ratio of the focal lengths of the 2 lenses, the distances f1 and f2.
The difficulty for Galileo was grinding down the convex surface of his objective lens to make it as shallow as possible in order to maximize the length f1, because the longer he could make that, the greater the magnification of his telescope. Produced in just a few weeks, Galileo's telescope had a magnification of 8 times and was far more powerful than the original spyglass. All he needed to do now was cash in on his new invention. Ever the showman, on the 21st of August, 1609, Galileo climbed one of the city's bell towers. Obviously, he'd have used the stairs. At the top, in front of an assembled group of Venetian noblemen and senators, Galileo demonstrated his telescope. It was a sensation. Using it, the Venetians would be able to see approaching ships 2 hours earlier than with the naked eye. The military and economic advantage of knowing who was sailing over the horizon was lost on no one watching that day. 3 days later, as a grand gesture, Galileo presented his telescope to the Duke as a gift. In return, he was guaranteed his job for life at double his salary. With his finances now secure, Galileo went on to develop a more powerful telescope. And with it, used the ability to bend light to change our perspective on the cosmos. This is the book Galileo published in 1610. It's called Sidereus Nuncius, which in Latin means the starry messenger. In it, he recorded his first observations of the night sky, the first anyone had ever made using anything other than the naked eye. Today, it's hard to imagine how anything contained in this little book was controversial. But you have to remember that back when it was written, the nature of the heavens was thought to be knowable only to God, and the Earth was considered to be at the center of the universe. These are his drawings of the moon. Since ancient times, all heavenly bodies were thought to be perfect spheres, but with his telescope, Galileo saw texture in the surface of the moon. Deep craters and mountains that, from the shadows they cast across the lunar surface, he estimated to be some 6 kilometers tall. As well as showing the heavens to be imperfect, his telescope began to uncover their true extent, revealing 10 times more stars than are visible to the naked eye. And in the final chapters, Galileo reports the discovery of 4 stars that appear to form a straight line near the planet Jupiter. His drawings show how their positions change from night to night. Although they moved, they always did so along the same straight line. And from that, Galileo deduced that they had to be orbiting Jupiter. They weren't stars at all. They were moons. Through his telescope, Galileo had seen evidence that overturned the accepted dogma that the Earth was the fulcrum about which everything in the universe revolved. Seeing moons in orbit around Jupiter meant that not everything went round the Earth. So, far from being the center of the universe, the Earth was just another planet. The telescope had allowed Galileo to glimpse the true nature of the cosmos and our place within it. But this way of manipulating light had another powerful application, one that would allow us to see into another world. In 17th century London, one of the most prominent scientists of the age was using lenses in a very different way. Robert Hooke had taken the basic principle of the telescope and used it to build a microscope.
Galileo uses the telescope to discover a new world in the heavens, and Hooke uses the microscope to discover a new world in the very, very small. But there's a difference, because what Galileo had presented was a world that was bigger and more plentiful, but it was a world that people were at least vaguely familiar with, because you can look up in the sky and see the stars. Whereas the world that Hooke presented was really something spectacular and new. It was a world inside the tiniest particles of matter that no one had ever imagined to be there before. People didn't even realize that there was a microscopic world there to reveal.
Hooke trained his microscope on a huge range of materials and living things. But it was his drawings of the exquisite detail he saw in the bodies of insects that would become famous.
So up here you can see a human flea, Pulex irritans, a very tiny creature. And then here we've got the plate from Micrographia, which is a huge image of the flea that Hooke produced. And it's really something spectacular. And this would have folded out in the book, so it was really very large. Some people said it was as big as a cat.
It's a work of art, really. I mean, there's just so much intricate detail in there.
It is, and there was nothing like it before Hooke. They really were unprecedented. And the shading and the quality of the images is just superb.
And it's accurate. I mean, it's...
It is, it's absolutely accurate. I was looking yesterday at images of photographs of the flea, and there's really, actually made with an electron microscope, and there's really nothing to choose between Hooke and the current images. This is an image of the compound eye of a fly, which Hooke shows in amazing detail for the first time. And this is an image of the foot of a fly. Hooke shows you the foot has little spikes in it that allow it to clasp into the pores on a surface.
Now, this image looks less interesting, less intricate than the others.
Well, it doesn't look terribly interesting, but actually it's really quite a profound picture, because what Hooke is looking at here is a very thin slice of cork, which he cut with a penknife, and he's looking at the little individual components that make it up. And he calls them pores, and then he calls them caverns, he calls them boxes, and then he calls them cells. And cell, of course, is the term that stuck. These are the little constituent parts, not just of cork, but of all living things. And so it's actually a profoundly important discovery and a name that has become standard in biology.
Using glass to bend light revealed our true place in the universe. And the intricate architecture of the microscopic world. The The more we looked, the more we saw. With each new insight into the nature of light came a fresh understanding of the cosmos. And the next discovery would take us far further and enable us to read the story of the stars. And it began with something Hooke had glimpsed through his microscope.
This is Robert Hooke's book, The Micrographia, published in 1664, 350 years ago. It's full of his famous diagrams. Here's his picture of the flea. It's incredible seeing it in its original form. It really is the size of a cat. These images really captured the public imagination and they made the book a sensation. But for me, the Micrographia is about much more than that. The chapter that interests me as a physicist is one that contains hardly any images at all. And it's this one here, of the colours observable in Muscovy glass and other thin bodies. Here, Hooke describes the iridescent patterns of rainbow colours he sees through his microscope as light passes through thin materials, like soap bubbles and Muscovy glass, a silicate mineral that's made up of lots of thin layers. At the time, it was thought that white light, like sunlight, was pure, that it came directly from God. And so Hooke concluded that the colours he was seeing must have somehow been added to the light, that they were effectively created as the light passed through the materials.
But Hooke's theory about coloured light was about to be challenged by his greatest rival. Isaac Newton is one of the world's most revered scientists. Best known for his theory of universal gravitation. And just like his laws of gravity, Newton's discoveries about the nature of light are among his most celebrated achievements. But the story of how that work began is much less familiar. And this time, there was no fruit involved.
This is Stourbridge Common, a sleepy riverside meadow on the banks of the River Cam. But when Newton visited in 1664, it would have been very different. For over 700 years, every September, this place would be transformed into what was, at its height, the largest fair in Europe. For several weeks each year, people would descend on the common for an annual festival of commerce and debauchery. This whole common would have been packed with makeshift stalls, farming produce, brandy houses, goldsmiths, silk merchants. There'd have been slack rope dancing, puppet shows, music, temptations of every kind, packed into row upon row of wooden booths and tents. Stourbridge Fair was a place you could buy anything you could imagine. But when Newton came here, it's said he bought just one thing, a prism.
He bought it because it performed the same magic Hooke had seen with his microscope.
Newton would later write that using his new purchase, he would try the celebrated phenomena of colours. a rather understated introduction to work that would produce one of the most profound insights into the nature of light.
Newton devised an ingenious experiment to discover precisely how these rainbow colours were produced, and to put Hooke's theory that they were created by the prism itself to the test.
This is Newton's own drawing of what he called his crucial experiment. In it, he arranged a prism so that sunlight coming in from a small hole he'd made in the shutters of his bedroom window passed through it and projected coloured light onto a screen. Well, here's my light source, and here's my prism, which if I arrange carefully, I can get projected onto the back pillar. Of course, none of this was new. People knew that prisms produced coloured light, but what Newton did next had never been done before. He first isolated one of the colours using a slit. So, in this case, the orange light. He then passed that orange light through a second prism. Now, if Hooke was right, then this prism should add the other colours to the orange and reproduce the rainbow. But all Newton saw was orange light. The prism wasn't adding any extra colour. He concluded that the colours must have been contained in the white light in the first place, that white light wasn't pure and prisms don't add anything to it. Instead, they split it up into its constituent parts.
Newton named the colours that make up white light the spectrum. And when this discovery was combined with the telescope, it would show us something remarkable. The spectrum would reveal precisely what it was we were looking at out in space.
This is a spectroscope. As sunlight comes in, it's broken up into its constituent colours and spread out much more finely than you'd get with a simple prism. Now, with this camera, I should be able to show you what I can see. I'll just check that it's working. Yes? Okay.
When scientists first did this in the middle of the 19th century,
Placing the spectroscope on top.
they saw something completely unexpected.
You can see the colours of the spectrum as Newton would have seen them. But if you look more closely, you can see something else. It's not continuous. It's broken up by lots of thin black lines. These are gaps in the spectrum. It was soon realised that these gaps were due to atoms in the outer atmosphere of the sun absorbing certain wavelengths of light coming from its interior, and that they could be used to work out the chemical composition of the sun.
Every element absorbs a unique pattern of wavelengths, an optical fingerprint that can be used to determine the chemicals that make up any bright object you can see in the sky. And in Rome, one man was using this technique to study light whose origins lay far beyond the sun.
Father Angelo Secchi was no ordinary priest. He was charismatic and viewed as something of a heretic by his fellow Jesuits. And that's because he was also a professor of physics with an evangelical passion for astronomy.
In 1852, Secchi was appointed director of the Vatican Observatory. And within a year, he'd built a new observatory on the roof of St. Ignatius Church in the heart of the city.
At the time, most astronomers were interested in mapping the positions of the stars and charting their motions across the heavens. But Secchi was different. He wanted to know what they actually were. So, from his vantage point high above the streets of the Eternal City, he began to meticulously analyze their light. Fitting a spectroscope to the observatory's telescope, Father Secchi laboriously recorded the spectra of more than 4,000 stars. This is Secchi's book, La Stella, The Stars, which he published in 1877. And flicking through it, you can see many of the observations that he made. This one in particular is interesting. It shows some of the spectra he recorded. The top one here is from the sun, but the second one is starlight. It's from Sirius A, the dog star, which is the brightest star in the night sky. It's 8.6 light years from Earth and over 20 times as luminous as the sun. You can see from its spectrum this clear sequence of bands, which is the signature of hydrogen, because it's a relatively young star. The universe's hottest, brightest stars have spectra rich in the two lightest elements, hydrogen and helium. But as they age, they cool, and their spectra reveal the presence of many heavier elements. This third one is from the star Betelgeuse, which is a red supergiant. It's near the end of its life, and so you can see from the many bands here that it's composed of lots of different elements. What's remarkable about this image is that, it really is one of the key moments in the history of astronomy, that we can learn so much about what distant stars are made of just by examining their light. But because Secchi had catalogued the spectra of so many stars of different ages, his observations led to something even more profound. That by analysing starlight, we can determine the star's life cycles. When they were born, and when they'll die. Understanding the spectrum had allowed us to read the story of the stars. It's quite incredible to think that what began as a simple experiment in a darkened room could reveal so much about the universe. That the scant light from those tiny points in the night sky could contain within it the epic drama of the heavens. But that wasn't all the spectrum could tell us. Today, we know that it's made up of light of many different wavelengths, and that those wavelengths extend way beyond the range we can see. The spectrum, from the longest wavelengths used in radio communications to the very shortest wavelength gamma rays, covers a range of 30 orders of magnitude. The longest are 1 followed by 30 zeros bigger than the shortest. That's the same as a spread and range of weights, from that of a single grain of sand to the weight of all the water in all the oceans on the planet. And within that vast spread, visible light, the frequencies we can see, covers a factor of just 2. That's the same as the difference in weight between this pebble and one twice its size.
Are we all set, Doctor?
Yes, I think so.
And throughout the 20th century, opening our eyes to the full spectrum revealed even more of the universe.
If you had infrared eyes, here's how the sky would look.
Infrared allowed us to see the universe's coolest stars, while radio telescopes, sensitive to the longest wavelengths, revealed a cosmos in turmoil.
It's the violent events that are picked up, exploded stars and galaxies.
And satellites have scoured the heavens for short wavelength ultraviolet.
The OAO picks up the ultraviolet light from hot stars, which the atmosphere cuts off from ground telescopes.
And here's the very latest window, gamma rays, which are like very energetic X-rays.
Seeing beyond the visible has allowed us to peer deep into the cosmos.
I was cock-a-hoop about this.
I too was wildly excited when I heard of this discovery.
But the very fact that light had proved such a useful tool for exploring the universe depended on one of its most mysterious properties.
Light behaves like a wave. But if it is a wave, what is it a wave in? Waves are carried across the ocean by the water, and the sound you can hear now is due to waves in the air. In the vacuum of space, there is no air, so there is no sound. But the reason you can see me is because I'm lit by sunlight that has traveled 150 million kilometers through empty space. So what is light? And how can you have a wave in nothing?
Answering that question would not only reveal what light is, it would ultimately allow us to glimpse the beginning of the universe. And the first part of that solution was a discovery that challenged our most basic assumptions about how we see the world.
To our eyes, light appears to be everywhere instantaneously. As I look out at the view, there seems to be no time lag, no delay while I wait for the light to reach me. But towards the end of the 17th century, it was discovered that our senses are mistaken.
In 1672, the Danish astronomer Ole Rømer arrived in Paris to begin work at the city's observatory and to continue his observations of the moons of Jupiter. For more than a decade, Giovanni Cassini, the observatory's director, had been documenting their orbits in minute detail.
Jupiter's innermost moon, Io, is known to make a complete circuit around the gas giant once every 1.77 Earth days. That's every 42.5 hours. Now, from Earth, we can see it disappear behind Jupiter and then re-emerge around the other side as it travels around in its orbit. But here in Paris in the 1660s, Giovanni Cassini had noticed that the timing of these eclipses seemed to vary, sometimes sooner, sometimes later than expected. Soon after he arrived in Paris, Rømer noticed that these fluctuations weren't happening at random. When the Earth was closer to Jupiter, Io would be seen to disappear and re-emerge earlier. But as the year went by and the Earth moved in its orbit around the Sun so that it was further away from Jupiter, then the eclipses appeared to happen later than expected. Romer knew the Moon always took the same time to travel around Jupiter. His great insight was to realize that the variations were due to the fact that light itself takes time to travel through space. Here's how it works. The eclipses of Io appear later than expected when the Earth is further from Jupiter because light takes a longer time to cover the greater distance. But they appear earlier when the Earth is closer because light needs less time to reach the Earth. Light isn't instantaneous. It travels at a finite speed. Today, we've not only measured light's speed with incredible accuracy, we've seen it in motion. This is a video made by scientists at MIT using a camera designed to monitor extremely fast chemical reactions. It has a shutter speed of around a picosecond. That's a millionth of a second. The time it takes light to travel just a third of a millimeter. Now, look what happens when I press play. What you can see here is a pulse of laser light moving through a water-filled bottle. To us, this would appear as the briefest of flashes. But the camera reveals how the pulse travels through the bottle, scattering and bouncing around as it hits the water molecules. Light travels so fast, 300,000 kilometers per second, that slowed down by the same amount, a bullet would take an entire year to travel the length of the bottle. It's one thing to know that light travels at a finite speed, quite another to actually see it move. The discovery of the speed of light was hugely significant. Not least because it proved crucial to uncovering what light actually is. Born in the summer of 1831, James Clerk Maxwell would become one of the leading lights of 19th century physics. His work on electricity and magnetism was one of the greatest achievements of the age. This is Glen Lair in southwest Scotland, Maxwell's family home. While he was growing up here, he developed an insatiable curiosity about the world around him, a desire to understand nature that he would never lose. The young Maxwell seems to have taken great delight in tormenting his parents and his nanny by constantly asking them how things worked. "What's the go of that?" he'd say. And if anyone ventured an answer, the young Maxwell would only be satisfied for a moment before asking them how they knew. Of course, none of this is particularly unusual for a child, but what sets Maxwell apart is that he was just 14 years old when he wrote his first scientific paper. So young that a friend of the family had to present it to the Royal Society of Edinburgh on his behalf. Maxwell was one of the greatest scientists who ever lived,
and it was here that he carried out his most important work.
During the 1860s, Maxwell produced a virtuoso piece of mathematics that showed electricity and magnetism were different aspects of the same thing. But his calculations would show something else. Quite by accident, they would reveal the true nature of light.
These are Maxwell's 4 famous equations that describe the relationship between electric and magnetic fields. Curl of E is minus dB by dt. E is the electric field, B is the magnetic field. Curl of B over mu naught div of E equals 0 equals epsilon naught equals naught. With a bit of algebra and manipulation, these 4 equations can be combined to give one single equation. So the way it's done is like this. We take curl of E.
Hidden deep within his mathematics was something that even Maxwell didn't expect.
Minus del squared E epsilon naught rad d2 div. This second term is 0, and I'm left with del squared of E minus mu naught epsilon naught d2E by dt squared. This is the wave equation. It tells us how an electromagnetic field travels through space. Now, the important bit is this here, mu naught epsilon naught, because it's related to the speed that the wave is traveling. In fact, the speed is given by 1 over the square root of mu naught epsilon naught. And if you work that out, you arrive at 3 times 10 to the power 8 meters per second, or 300,000 kilometers per second, the speed of light.
If electromagnetic waves moved at the speed of light, it could only mean one thing.
Maxwell knew this had to be more than just a coincidence. It meant that light itself had to be an electromagnetic wave.
The discovery that light is an electromagnetic wave explains one of its most puzzling properties.
What Maxwell's equations show is that light consists of electric and magnetic waves traveling through space. So light is simply electric and magnetic vibrations feeding off one another as they move. And we now know that these electromagnetic waves have a remarkable property. They don't need to be waves in anything. They can travel through empty space. I remember first learning about this when I was in my second year at university. I was in lecture hall 33 AC21 of the physics department at the University of Surrey. The lecturer was Dr. Chivers. And I remember turning to my friend next to me and remarking on how incredible I thought this was. And I could tell by his reaction that he thought I was a bit of a geek. But actually, it is incredible that in just a few lines of algebra, you can tell what light really is.
And the fact that light travels at a finite speed has enabled us to do something else. It allows us to look into the past.
Looking at a mirror 1 meter away, you see yourself as you were 6 nanoseconds ago. From Earth, the moon appears as it was 1 second ago, and the sun 8 minutes in the past. The further you look out in space, the further you look back in time.
Light from the cosmos's most distant objects has taken billions of years to reach the Earth. But there's one source that has taken us so far back in time, we've reached the very limit of what can be seen with light. In 1964, while converting a strange-looking horn antenna designed for early satellite communications to make astronomical observations, Arno Penzias and Robert Wilson began to pick up a mysterious signal they couldn't explain.
Here we had purposely picked a portion of the spectrum, a wavelength of 7 centimeters, where we expected nothing, or almost nothing, no radiation at all from the sky.
Instead, what happened is that we found radiation coming into our antenna from all directions. It's just flooding in at us, and clearly was orders of magnitude more than we expected from the galaxy.
At first, they dismissed it as noise, something unwanted generated by the antenna itself.
Now, we had some suspicion because the throat of the antenna came into the cab and was a little bit warmer. And that was an attractive place for pigeons, at least a pair of pigeons who like to stay there, especially in the cold winter. We didn't mind that because they flew away when we came, except that they had coated the surface with a white sticky material which might not only absorb radio waves, but then emit radio waves which could be part or maybe all of our result.
With the antenna cleaned and the pigeons, well, it didn't end very well for the pigeons. Penzias and Wilson began searching for an astronomical explanation. But the signal wasn't coming from anything in our own galaxy, nor did it appear to be coming from any other galaxy. It seemed to be coming from everywhere.
No matter when we looked, day or night, winter or summer, this background of radiation appeared everywhere in the sky. It was not tied to our galaxy or any other known source of radio waves. It was rather as if the whole universe had been warmed up to a temperature about 3 degrees above absolute zero.
And so we were left with the astonishing result that this radiation was coming from somewhere in really deep cosmic space, beyond any radio sources that any of us knew about or even dreamed existed.
What they discovered was light so ancient it had been stretched out into microwaves and cooled to just a few scant degrees above absolute zero. Light that had been traveling to Earth for almost the entire age of the universe. It hadn't come from a distant galaxy, and it was far older than any star. Penzias and Wilson had discovered that the entire universe was awash with light from the embers of the Big Bang itself.
Called the cosmic microwave background, it was released when the universe was just 370,000 years old. And it gives us a snapshot of the cosmos in its infancy.
And here it is, the latest image of the cosmic microwave background, taken by the Planck satellite and published in early 2013. The different colors are fluctuations in temperature in the early universe, and the information they contain has proved priceless to cosmologists.
The tiny variations in temperature are caused by matter clumping together into what will eventually become stars and galaxies.
But what's truly remarkable about this image is that it's not just light from the early universe.
It's the very first light there ever was. During the first era of its life, the universe was a fireball of hot, dense plasma that trapped light, preventing it from moving. Then, as the cosmos cooled, the plasma condensed, forming the first atoms. And the first light that would become the cosmic microwave background, was released into the universe.
It's sort of hard to express what an astonishing achievement this is, that from our small planet, orbiting an unremarkable star, we've reached out into the universe and seen as far as it's possible to see with light.
The discovery of the cosmic microwave background appeared to complete our picture of the universe. The final chapter in our use of light to explore the cosmos. Understanding the nature of light has allowed us to illuminate our world. We've captured it from the depths of space and the beginning of time. At the smaller scales, light has uncovered the microscopic structure of living things, and at the largest, it's shown us our place in the cosmos and told us the story of the stars. Virtually everything we know about the universe, we know because it's been revealed by light. But just as it seemed light would lead us to a complete understanding of everything, in the last 30 years, it's shown us something disturbing. The vast majority of the cosmos can't be seen at all. Far from being a universe of light, much of it is hidden in the dark. Next time, how scientists came to the realization that more than 99% of the universe lies concealed in the shadows, and the extraordinary quest to uncover what's out there in the dark.
Whether you want to step into the light or explore the mysteries of the dark, let the Open University inspire you. Go to bbc.co.uk/light and dark and follow the links to the Open University.